All right, so good evening, everyone. In this session, we are going to discuss week 9 topics. At least we'll try to start with that, right? And I'll try to also highlight important parts coming from week 9 because there is a clear distinction, between this week and the prior weeks that we've all been seeing so far. So it is important to highlight some aspects which are unique to this week and the topics that are discussed herein. That is one. The other is that I would advise all of you to go through the previous live sessions which we have curated for the weeks, like specifically for week 9, right? So therein we have already done a detailed discussion regarding all of that, but again I'll go through that, and I'll kind of expand upon, to the extent needed, expand upon the topics that are there. But again, if you want to kind of go through it in complete detail as such, then you can go through the recording as well. But again, I mean, you're free to ask questions. We're here to clarify as much as the doubts that you may be having. Okay, so there's no issue in that. The other thing is, so before we get there and start with week 9, I just like to take a stock of how was quiz 2 for all of you. Okay, I see Naren is giving a thumbs up.
Made
So,
some silly mistakes, sir. Otherwise, it was okay.
okay, what was that silly mistake that you made, if you don't mind sharing?
Yeah, the dart question, I thought
uh
once actually it was greater than it was coming. So I
mhm.
misunderstood and written as greater than or equal to. I mean, less than or equal to. The answer
Okay,
says,
okay.
I remember sometime somewhere you were telling at the line one,
Mm-hmm.
whatever concrete
Mm-hmm.
values are given.
Mm-hmm.
If it passes, what will be the second one? It will
Okay.
be something like that.
The next execution you gave, is it?
Yeah, I gave the next execution.
Okay, okay, I
So
see.
I suppose after the answer, I could see at the same
Mm.
level what was the execution. The last
The question
question.
was
Yeah,
this execution. No, so I mean that is, I do
you
understand.
told
It's
101 times, sir. Actually,
this and
you
next is
repeatedly told that, but I still
yeah.
missed it.
No, no, it's okay. It's okay. I mean, it's not. I think it's not your fault. To some extent, this versus next is a very very subtle difference. Actually, no, very subtle difference, and we have to be very careful about that. That is one. We'll try.
Yeah,
We'll try from our end to also make it explicit. The thing is, see, the thing is, if you make it so like so apparent,
easy.
no, then there is no point in asking that question even, no? So we just kind of keep it like that, so the balance is there, so that it does not become ambiguous, while at the same time it tests you whether you know the concept or not. So the very nature of working of dart, what it does is just does it for one, like for one part of it, and then it negates does the other part of it. So it is like the usual thing that you have. Maybe what we can do is we can ask for both or something like that, but again I'm not sure on that, how will we go going. But again, yeah, so that needs to be kept in mind actually. Okay,
And I
that was
think I am having that question doubt, sir. What last sentence you are telling? No, like see, in this question it was asking.
mm,
Um, can I share my screen, sir?
yeah, if you want to you can, it's
Yeah,
fine.
I will just share, sir, so that once for all I will get it clarified.
Mm,
Are you able to see my screen? No. Yeah.
not yet, should be
Yeah,
coming up,
it
I
has
think. Yeah,
come.
now it is there. Yeah,
So this question
yeah.
actually a 4 is greater than 2, so first and it will pass. Then
Okay.
it says 64 minus 32 is saying
Mm-hmm.
64 minus 4 for 16 twos are 32.
Mm-hmm.
So, okay, I think I did this right. Mm. So it is 32 is lesser than, I mean, 64 is greater than 32.
So it'll be greater than zero, right?
Yeah, greater than 0, correct. 32 is greater than 0. So
Yeah.
for that, already random input has been given greater than 0.
Mm-hmm.
So next execution, okay, next the word
So we
again
are
is
asking for this one, right? Okay.
okay. This one,
Yeah.
sir. So
Uh,
it will be, how is this?
so this is
Next
the path
execution
constraint corresponding to this execution,
line.
not the next. Because if we have to give the negation, then it will be for the next execution. See, we are saying for this execution. That is,
Yeah.
you see.
So this will be the for going to the abort statement. This is correct.
This is correct because this is even more direct. So it is saying that how would you
Direct.
reach that? No. So that is what you have.
Yeah,
Okay.
I remember we were discussing next execution like that. Same
Ah,
line it is asked. I was so clear when you explained, and exam. I
right,
think
right.
I think I made a mistake. Only the answer script will
Uh-huh.
tell
No,
what
even
is
the
being.
calculation, no, sometimes it causes because the calculation is slightly involved, not very much, but we kept it to
Sir,
quadratic this thing. This is the
I still remember the
determinant.
calculation, sir.
Yeah, so this is
Without
b
even
square minus
seeing
4
this,
AC.
I remembered.
Uh-huh. So this is b square minus 4 AC, and if you get a negative, then you got complex roots and so on
Yeah.
and so forth. So you're borrowing from there. Okay, all right. So I see Vasu has joined in also. So I would appreciate
Sir,
your take on the
later on, if
quiz.
time permits, can you explain
Which one?
these questions, sir? PSP.
Yeah. Can you go to the table, please?
Yeah.
Table. Yeah, they're asking for RICC, no? What is that? GICC or RICC? I didn't
No,
get that.
RACC, I was able to, it was
R
very clear.
GICC, okay?
This GACC and
RICC, right?
RICC,
I think both answers are same, isn't it? Like 1-3-1-3 for both. Hopefully, it is the
Yes, sir.
yeah, 1313.
yeah, because it turns out there's only one GICC pair even, or at least from the options what you
That
have, right? So,
that
so
line one also I didn't. I don't know. I think I made a mistake. I didn't pay attention.
oh, is it?
No, here if you say GICC of
Hmm.
for GICC for class
B.
B. So
Mhm.
B, whether it is true or false, your predicate should not change. That is
Yeah,
the
and PB
understanding.
should be false. PB is false, right? The B should not be active, right? That's what inactive means. So PB should be false. So you only got 1-3, right? Straight away.
Okay, okay. So I did not consider this last
Yeah.
three columns
Inactive
is
means that, no? Yeah. You have to, right?
but
So
still okay.
determination. Yeah.
But inactive again, one more thing you can say is when B is true or B is false,
Hmm.
there should not be change in the predicate. Is that
No,
correct
no,
way of
no,
telling?
no. No. GACC or GICC has nothing to do with the predicate.
Hmm.
It has nothing
Okay.
to do with the predicate, right?
Hmm.
So for A in GACC or RACC, CACC, you have to take whatever predicate you're interested in, P, A, whatever clause A, B, C. You have to take for A active, you have to take only the rows where it's active, which is PA or PB or PC is true. For inactive, you have to take only where it is false. So automatically they'll get filtered, right? So PB, all the active clauses, GACC, RACC, CACC will be limited to 2, 4, 5, 6, 7, 8. All inactive will be restricted to 1 and 3. After that, GACC has no further or GICC has no further restrictions. You just look at A once it's positive, once it's false, right? You take whatever is available, you take all those cross products. CACC has additional restriction where the predicate has to change. Overall P, not PA or PB.
Yeah,
Overall
this is for
predicate has to
active,
flip.
right?
Yeah, for active. For active. There's no CACC for
Also,
inactive.
sir,
GICC.
active was okay. I mean, if it is inactive, directly what is telling is PB should be false. So only there are two rows.
Yeah,
So
yeah.
it
In
is a
this
direct
case,
question.
correct. In this case, there are only two. In other cases, there could be more.
Okay, so I was thinking of inactive means predicate should not change. Active means predicate should change. No, sir.
That
No,
is
no.
correlation.
That is correlation only. Okay.
Yeah,
I think for end term, once again, coming back to the
Yeah.
same
No. So
thing.
we'll revise this thing again. So I've
Yeah,
been mentioning this. See, the thing is, determination is not correlation. Okay, determination is active versus inactive. Now, if you're doing active, then determination should be true. If you're doing inactive, then determination should be whatever the conditions are should be false, right? PA, PB, whatever. That is inactive versus active. That is one part of it. Correlation is the actual change of predicate. Okay, so therefore CACC, right? The very word, the very term itself, no, CACC tells us that it is both correlated and active, right? How it could be. If active means correlated, then we cannot have CACC. See, CACC is there just to say that we have correlated plus active. We have that
correct.
distinction there, right? So that's why it is there.
One
So
trivial question, sir. I mean, doubt, trivial doubt. After that, I could understand. See, even the manager is a user, no, sir. Actually, in this question, if you go see,
hmm
store manager also using the app or the website,
okay.
no.
Yeah.
Can't it be a user requirement? User only, customers only can be taken as a users actually.
Yeah. So there's this concept of
B-
primary, tertiary, this thing, right? Primary,
yeah,
secondary, tertiary. We're taking it from there, from software engineering. But then we have specifically mentioned that customers are the users, and that
Exactly.
even then, you don't have a user requirement there, right? We just didn't have that
it is
option,
more like a internal stakeholder.
Yeah. So
Usability, it is not usability.
no, it is not. Usability is
No,
that, no accessibility. If screen
Okay.
readers and other equipments
I
can
think
read
I
it, read
wrote
websites.
non-functional requirement.
Okay. Non-functional. See, the thing is, yeah, there's some other student also was mentioning that. So the thing is, I just make it very clear to for all of you. The thing is, see, function is when something happens. Some feature, some objective. Some input output processing happens. That is a function, right? But non-functional is which is not directly related to the function in the program. So let's say appearance, right? How good something looks like, or how performant it is, or how quality parameters are. All these things are non-functional, meaning it is not having a function, it's a form. Think about it this way, right? Design versus
Color.
implementation, function versus form. This is a form versus function question. So non-functional things are form, related to the form of the thing, right? Form of the software, whether it is quality, how it is, how the quality is, how it looks like the appearance and stuff like that.
The
Whereas,
color can be color, green base,
ha,
or it can have Times
right,
India, Times
right, right.
Roman.
Right,
Those
right.
things are
Those things are
non-functional.
non-functional. Yeah. As soon as you see something happening, no. Now there are two levels to it. One level is something happening or not because of this feature, no. Is it the data, some data processing is happening or not? If you think about it this way, is there a functionality involved? Then it is a functional thing. Now, when it is a functional requirement, under that, depending on this, now the stakeholder comes, right? So a broad classification is functional, non-functional. Functional is wherever something is happening, so it is functional. Non-functional is which is not related to the functionality, rather with appearance and stuff like that. That is one. Now within functional, depending on the stakeholder, it changes. So if the user is, the primary beneficiary, so to speak, is the user, then it is a user requirement. It's a business imposed requirement, then it's a business. So we said a store manager should be able to download monthly sales report, right? Sales report. So you get the idea that, okay, sales report, who is getting benefited, business, and stuff like that. So you have to just kind of read through the lines and understand it a little bit. Okay,
Yes, sir. Thank you, sir.
that's
So
what
those four
happens.
questions only, I think I got wrong.
Oh, okay,
Naren,
okay.
can you go to that question where you have that state of the variable Ri? There, I think I made that mistake. You were sharing the paper, right?
Sure, sir. I'm doing that
Yes.
again.
Please, thank you, my friend.
Yeah.
I debated so much. I got so confused in the exam, and I wasted almost like I took almost
Which
five, seven
question?
minutes in that the
Yeah, I also
this
took a lot of time, but the concept itself I have not understood. That is
not
my mistake.
not this the Ri no the 0 to 1
One.
this one
Yeah,
this
zero.
one.
Yeah, see zero when it's starting. Yeah, here you can see, sir.
See, what I did was I really like really broke my head. Literally, I wrote down how the array will look like from. I think I ticked the next one, which is 1 to n. Okay,
No, 0 to n.
0 to n because I yeah
Okay.
0 to n correct. I don't know why I did
So
did
So
I
when I
do. I
equal
am
to
not
zero, n
confused.
equal to zero, it will be directly going to return the
No,
product.
I got yeah. So actually, if you look at the count, n-1 to 0 plus 1 should be n. Now I don't recall what I did actually. Now I'm forgetting.
yeah.
See,
So
the
the thing
third
is,
one I got confused because
hmm,
see the in the loop I is immediately updated,
hmm, hmm,
right? So I thought it will become one immediately even before you check for the system for whether it's true or false.
yeah, okay.
So had it be so
Hmm.
I don't know what I did it now. I have to check. I'll have to wait for the answers. So
Okay. No, so that's okay.
I thought it should not start with zero.
Yeah, okay. That's a good assumption to make if you have another option. You only have zeros, right? So
Yeah. So I don't know. Maybe I confused that thinking with this. I don't know what I did eventually. Maybe I
yeah.
did
See
zero to n is patently. If I did that, that's a complete oversight because 0 to n is n+1 variables. Right?
exactly.
That's
That's
not
the key
possible.
point. Yeah.
That's
That's the
not
key
that
point.
should
Yeah.
not be possible.
Because what are
But
we
I may
saying here?
have
Hmm.
I may
Fine.
have done that.
Okay. What are we saying here is that we want to have n true outcomes. No, n. So n is like a
Yeah,
quantity,
that's
right? So it's like a
yeah,
quantity. So I
it's
say 10 times I want to make it true, then it will be 0 to 9. No, 0 to 9. So
yeah,
that
no, no, correct, correct.
then
It's totally
yeah,
stupid. If I over, I think I over
yeah.
like
You were thinking about
We
it too much
overemphasized
here.
discussed
on
this,
that
Vasu
and
sir.
probably tick the huh.
Vasu sir, we discussed this. Even when initialization is some n, I mean m or k or something, it will be k plus n. In some other in the
Correct, correct.
lectures
But I
here.
plus one was coming first, so I thought it should start with one ideally. Ideally, if it had started with one to n, it would have been correct in my mind.
Correct. Yeah,
Okay, so
this one.
I probably confused it. There's no one, so that's not an option. I
Yeah.
hopefully I don't remember, but I hopefully tick the right one. But I was thinking on those. Is that even correct? Like ideally, I is already one before you test the first two.
Makes sense. Okay. I get that. Yeah. Yeah. If you think about it that way, then it is one. But then again, you have to, you have to end
No,
at
no.
n.
Here for see this these answers are consistent with n trues and n one false. That is
Mm-hmm.
correct. But I'm saying if you really become very pedantic about it, shouldn't it be one and n? Just for my own logical understanding. That's it. I'm not pointing out any mistake at all.
Okay. I belonging to because you're not checking for the zeroth case, right? Okay. Yeah. I mean, you are correct. I think you are correct. Yes. Had one been
No,
there,
but sir, how sir? I is zero only. You are
No, no.
starting
You
the
he's saying that
correct.
before we check for it,
You go into the loop. The first thing you do is you have updated
increment.
I. By the time you're checking for true or false, I is already one.
Makes sense. Yeah. Yeah. Because then R symbolic input becomes RI rather, right? So RI is R1
Correct. Correct.
by that time. Yeah.
Correct.
Makes sense. Yeah, yeah. This will look into. I don't think we can change the answer given the fact that it was already zero. But
No, that's fine. That's fine. I'm not saying change the answer at all. I mean, that
yeah,
option doesn't exist. I'm just
yeah.
saying I was like I actually spent a lot of time thinking that will that change? Will that does
Mhm.
that mean I should look
No,
at
no. Ideally, this I plus plus. No, it should have been the last statement
correct?
before
after
the
Then
the
it's fine.
uh,
Then it's fine.
because you are having it after the product happens. No. Okay. Okay. Yeah. This
so
is
I
noted.
think this question needs to be
Mm.
I don't know, you have to check up now, sir, whether it is right
Yeah,
or
I mean,
wrong.
as regards the options, it is correct only. But given given the code, maybe that's a slight
Then we
what
have
do
to
you call it? It's
discard
not
this question.
it is not agreeing with the assumptions given code, right? So I is see the thing is we are saying I belonging to 0 to n, and I is not belonging to like I is not 0. So that's I is never 0, right? Because I is 0 at initialization, but you get in and you that's I is never 0, right? Because I is 0 at initialization, but you get in and you increment it. So for that loop, it's not checked. Okay, okay. This is noted. We'll see what can be
Okay, sir, I'll
done.
stop.
Okay. Any other question from anyone else regarding this quiz paper? I think the CGPA question you all got correct. I think hopefully.
Yeah, yeah, we discussed.
Uh, okay.
We go from first, sir. This one okay, this one okay. All
hmm Boundary values. Okay, fine. Additional tests. Uh, yeah, this we mentioned up to one decimal place, no, to avoid ambiguity. That is. So you straight away
yes,
know
sir.
that the five, correct cases, and then you have more than 100 and more than 10 and less than
Yeah,
4.
less than 4 and more than 10.
Yeah, yeah. So 7. Okay. This one, yeah, I get Vasu's point is correct only. So we look into that. Yeah. What else? This is okay. Yeah. Three
Theory,
conjunctions.
this one,
This is
RACC.
RSCC. I think hopefully you got it right, right?
Yeah, yeah, RACC was,
Hmm.
ACC was okay, sir. Only ICC I had problem. And I don't
Hmm.
know, maybe others also.
Mm-hmm.
There are
Okay.
two
And
questions
since
this
GICC,
side.
there's only one GICC pair, no? So then immediately you know that RICC also that could be the only pair, right? I mean, it could only be 1 3 if it is
Yes,
this.
yes.
Yeah. Because
No,
for
one if you know what is ICC, then these two questions were easy.
Yeah, that's what. So we've been mentioning it, no? That PA needs to be
Right.
false or whatever for the inactive case. Okay.
Correct.
Yeah, this one, can you scroll down? Cyclomatic complexity, right? 3. How many
Yes,
edges are
sir.
there? 8. 8 minus
E
7 is
minus
n. 1 plus
E
2
minus
is
N plus
3.
2P.
Yeah, P is 1, so
Yeah,
this is 3. Correct.
1. Correct, sir.
This one we have to do. H pair, I don't know. We have to do that and then check. Okay, fine.
H pair
Um,
we counted.
hmm, okay.
Only
Yeah,
thing
but
we would have got is one uh, year 5-3, 5-4-3,
Two,
one
no,
loop is
2p,
there.
2p, right? Edges are 8. 8 minus 7 plus 2, 3, right?
3,
Answer?
right?
Yeah,
Yeah,
3.
that's
That's
correct.
correct.
That's correct. That's correct.
Now this H pair 3, 4, 5, and there is one loop. So you'll have last quiz one we had this loop problem, whether the H pair will come or not. Then
Come.
was
No,
It'll
last
come in.
that was different, Naren. That was self loop.
Hmm.
self
This is
loop.
not a
Okay,
Even
self loop.
even self loop is counted. Even self loop is counted.
counted
Yeah, yeah.
here. This one
Self loop we
loop.
got a little confused, but this we didn't. This
Okay.
was
Okay.
this was
This
fairly
is
clear. I mean, you can't, when you're doing it, you shouldn't miss that because it's a back edge, almost like a
Yeah,
back edge.
yeah. Okay, and then you have the test part. So this one is easy because this is not saying edge pair, mind you. This is just saying edge, right? Basic edge coverage. So
yeah,
so
yeah.
you just
That
look
will
at
be
that.
something like 1 to 7 directly. 1 to 7, one pair, one
Yeah, I mean you have to do that and check it.
into the
I think yeah.
direction, and the
Uh,
other one will be like full with the loop.
okay. All right. Okay then yeah. So if
That's all,
that
sir.
suffices, that's okay. And then
Yeah,
we can start with some discussion at least. Week 9.
yeah.
Uh,
Week 9 will go, sir.
okay. So let us just start. I'll just share
So
my screen.
top. Yes, sir.
Uh,
Thank you very much, sir.
Thanks. Okay, so let me know if my screen is coming up. Sometimes it causes a problem. So okay,
Not
hopefully
it.
it be there. Yeah, no, just give me one moment. It should be coming up. Is that okay?
Say it's come, sir.
All right. So this all we've discussed week 9. Okay, so there are two broad things in week 9. One is regular expression. Okay, and why we are studying regular expression is like a prerequisite to mutation testing. Okay, so the majority of the bulk of week 9 is mutation testing and the various aspects of it, but regular expressions are kind of like a prerequisite to it, so we are going to discuss that. Okay, so when you do mutation testing also, it might not be that you're directly taking it from regular expression as such, but it is good to understand like the background as to what are we doing with mutation testing in the first place. Okay, so I'll just go through this briefly to understand what it is. So the thing is in programming languages, it is all well defined, right? What is the syntax? It might not be true for natural languages, right? Because one thing may be said in multiple ways. I mean, that is true to some extent in programming languages also, but what I'm saying is that it is not it is not fuzzy, so to speak. The kind of languages that are there on computers, they have to be very strict or kind of very well defined, as opposed to natural languages wherein you have a little bit of flexibility in terms of what you say, and still you convey the same idea in some sense, right? I mean, there are ways of doing one thing one thing in multiple ways in programming languages also, but more or less it is all very well structured, and you understand where to put what. And even if something a little bit of changes is there, then the compilation process will fail and so on and so forth. So I hope you've all gone through that process doing Java and even Python and all such languages. So you understand the syntax, the idea of syntax. Okay. So far in the graph-based models, no earlier ones, we had seen the program. We were considering the source code, and we were doing the testing up until I think even week 6. You can 5 and 6 you can consider because we are looking into predicate. No, in logic we are looking into predicate. Week 7 also it is like automated fashion. We are traversing the source code now. Week 8 was black box. So here we did not talk about the actual source code, right? But now in week 9, we came back. So this is again white box, okay? Mutation testing has to be white box, cannot be black box, okay? Because we are not only analyzing the source code, as in the case with graph-based models or even logic to some extent, here we are even allowed to modify the source code. Now, one may wonder why modifying source code is helpful and so on and so forth. So hopefully that will become clear as we move forward. But that's the idea. We are even allowed to mutate or make change. What is mutation? Mutation is essentially making changes, right? So we are allowed to make changes in the source code of the program that has been given to us for testing. Okay. Now we'll see how it is helpful. So that is the idea. We are going to consider the syntax of the software artifact now. So far we were looking into structure, data flow, defs, users, and then we came to logic, predicates, branches, exploring the program, using symbolic execution. But we had not looked into syntax itself. So that is a new thing that we are looking into, right? And then we are even allowed to modify it. So the thing is, as in natural languages, even programming languages do have grammars. Okay, grammars are essentially, to put it very simply, this is just a set of rules, what is allowed, what is not allowed. So for example, in Java, there's a rule saying that, after every statement, you have to have a semicolon. If you don't have that, then it fails to compile even, right? It does not make sense. I mean, it does not matter whether you have the logic correct or wrong. Even if you don't have the semicolon, it will fail, right? So that is like part of the language, part of the grammar of the language. It will not accept any statement without that. So that happens. Now Python has a different syntax and so on and so forth. So that is the idea. Now there are ways of describing that grammar. Like, okay, I understand that. Okay, what is valid, what is not valid. Now think about it. I want to design a language. Okay, now if I'm going to design a language, then I need some way of expressing that, some expression. How is language? How are languages defined even? Right? We may not have like we have English grammar also, but that is again it's like a little bit fluid in some sense, right? But that is not the case with computer programming languages, wherein you have to have strict rules. So that is where grammars come into the picture, and we have some modeling of the language itself. Like how do we define that language? What is allowed, what is not allowed, and so on and so forth. So we are going to mostly revolve around that idea. Okay. So again, so BNF grammars are for programming languages. Modeling languages are there like XML and all. Right, are there. So yeah, here you have XML inputs, file specification, and so on and so forth. UML is there for modeling, like the class hierarchy and so on and so forth. FSM you have already seen, right? All these things. Okay. Now the idea is syntax can be, this is very obvious. I'm not going into much detail. It said can be used to generate artifacts that are valid and those that are invalid, because now you have a reference point. See, you have a rule, right? So if you say that something is from the language or from outside the language, or whether it is conforming to the grammar or whether it is not conforming to the grammar, whether it is conforming to the syntax or whether it is not conforming. So we can essentially then generate both valid and invalid artifacts. Now, in our case, in mutation testing, we are going to just talk about programming languages and not other kinds of languages like UML and all. I mean, we are not going to discuss that in detail. Mostly our discussion is going to be about source codes. Even though we have said artifacts here, the idea is basically source code, right? In this context, it is going to be source code. So the idea is that we can have invalid source code also from the perspective of what? From the perspective of the grammar itself. Now we are not talking about the business requirement or whether it is working correctly or not, or test cases. We are talking about the programming language, like is it syntactically correct or not, no? Whether the compilation succeeds or fails. So that is one aspect. The other aspect is also there of functionality, the usual test case, whether it fails or passes. So we'll come to that. Like we are building up the stage for it actually. Okay. So then syntactically something could be invalid or valid. Just keep that in mind, right? Right. So for example, in one statement you have missed that semicolon in Java, so that will be an invalid syntax, for example. Okay, very naive example, but that's what it is. Okay. Now, uh, the artifacts that they are there, the source code and so on and so forth, right? They themselves are not test cases, right? I mean, the program source code is not test case, then you have to generate test case based on that. Like for example, symbolic execution was doing that, no? Source code is there, it generates test cases for you and so on and so forth. Okay. So the source code itself is not test case. Okay. So that is one thing. So that point will become clear as we move forward. Okay. So the thing is, now we have grammars. I have briefly talked about what grammars are, and regular expressions we are going to see soon enough. Okay. So there are going to be coverage criteria. Again, the very nature of the way we are following testing, software testing. So there is this criteria. We say that okay, we are going to do this and this for testing. So we say that is the coverage criteria for every technique that we've been seeing so far. Everything has a coverage criteria, so we're going to cover. So similarly for grammar also, for regular expression also, we are going to have coverage criteria. Now once we have that, we have something known as mutation testing, about which we'll talk in a little while. So that also, like, this allows you to modify it. Okay, this is not just about coverage, rather it is also allowing you to modify. So far the tester has not been doing it, right? Me as a software tester would not be modifying the thing, right? Because the source code that is given to you, you're going to test it, right? But here we are allowed to modify also. And why is that helpful, and and so on. We were going to say it later. Okay. So again, mutation testing can be applied to test source code, design elements, XML inputs, and so on. We are mostly going to talk about source code in our discussion. Okay, but we'll come to that later. Now, a little bit of background about programming language syntax and so on. I think the brief overview of that already given. I have already given that, so it's fine. The syntax, you know what it is in general. Now, so syntax comprises of these three things mostly, right? So it is going to be words, like the the lexical level, like at the very base, what you have, how tokens are, well, not tokens, how the characters are forming tokens, right? Not tokens. You might be hearing a lot these days in the context of LLMs. So it's not that token that we're talking about, but yeah, you can think about it as roughly related to that token even, right? That LLM token that is there. Okay, regardless. So that was a tangent. Okay, now so we have words. So these tokens, no, are specified using regular expressions. Now what happens is these multiple tokens, then these words are combined together to form phrases. Now I'll give you a concrete example. Okay, so think about this int, right? In Java, int is a type. It refers to a type, right? In is a different keyword maybe. Int, if you make it int or you say integer, that has a specific meaning, right? In a specific context and so on and so forth, right? So that those are words, like how the characters are making sense. Why int? It could be anything else also, no? It could be called number also, but in Java it is called int for integer and so on, right? It could be complete integer also, meaning the complete word, right? It could not be a short form and so on and so forth. It happens now. So that those are words, like after the characters are forming the words. Now multiple words are combined to make phrases. So very basic, it might even be not directly correct, but I'm just saying very basic example could be, let's say you have something, integer n is equal to, and then you give a string there. So that's like a phrase that I'm having, right? Now integer n is equal to, and I'm giving a string there, with the quotation mark. So that is syntactically wrong in Java, because it will say you are giving a string into that. It's supposed to be an integer, right? So that is not the correct syntax. Then it'll fail, right? So phrases are more than words, right? Multiple words are combined together to make one phrase. Okay. So that is what it is. Now this, to specify phrases, we have also context-free grammars, about which we'll talk in detail in this BNF form. Okay. So we'll think about it. Now, context is also important. These are just words themselves, phrases themselves. Now, the context is also important. Now, so for example, the word int in Java, int, is okay, like it is syntactically valid as on its own, right? Now, when it is combined with a variable, let's say I call it int a, int space a, so that is also fine, right? But then, maybe int a is not available there, or something. Int a, you are not supposed to declare integer a there. Maybe there's another variable which is already there of that name. Integer a itself is fine, but if it is already declared, then you cannot declare it again. So that comes from context. That is the last thing, right? Because you have to have knowledge about what is going on there already before you can write things, right? So if, for example, you're calling a method, but that method is not there. So syntactically, it is correct. I mean, as regards the words, you are giving the method name, you're giving that parenthesis, so it calls. That is okay. But then maybe you are having a return something, return, and you're calling a method. That's also fine. But then context wise, it is not there. The method is not defined. So it will throw an error. So it is outside the grammar itself. Okay, it depends on the environment and so on and so forth. Okay, so that is also known as context sensitive grammars. So this one I think we are not going to talk about. Okay, we are mostly going to talk about CFG. That is not that CFG. This CFG is context free grammar. Okay, so we are just thinking about phrases and words. Okay, so the basic form is a regular expression. How do we define it? So for those of you, I mean, most of you are already coming from, I think all of you are coming from system commands, right? System commands, you've done that. So you know what regular expressions are in general. So that is a formal definition here that is given. So it says we have an alphabet, meaning some alphabets, it could be English alphabet, or some set of characters that are there. So that we call alphabet. So any regular expression could be part of that alphabet only. Now regular expression could either be empty. So this is the phi, empty, or it could be one letter, like one character from that alphabet where a belongs to a, this one. Okay, or it could be a summation. So we'll think about what all these operations mean. Okay, r plus r dot r, and r star. Okay, so this one we'll see. So now this is just the syntax, like how do we express it now? But semantics associate meaning to it, right? Like what happens after we, so there we call it a language. When some meaning is associated to an expression, then it becomes a language, right? Because expression could be anything, because if it is meaningless, then there is no semantic association, right? So there's no language associated with that. I mean, you can have anything written, using the English alphabet, right? It does not mean anything, but unless there's semantic associated with that, then you extract meaning out of it, right? So meaning comes from semantics, and that forms a language. Okay, semantics form a language. So it says about this expression, this how do you put it? Yeah, this basically this definition. It's saying that L of phi, so the language of, if you just have this in the regular, because the regular expression can either be of these things, right? And it's a recursive relation. So it says if it is empty, then you got an empty set, and this we are denoting in the set notation. So we will see how it is helpful. Okay, so L of A is just A, having just a set, having just a no. L of R plus R, so you have two regular expressions and you are doing a sum onto it. This one, this operation, right? Sum operation, plus R prime. So then it becomes semantically the language of R union with the language, because language of R you'll have a set, right? Some set, some regular expressions there, and you're going to get a language again, either of the two sets. I mean, some set you'll have, right? Then you're going to take a union of that with the other language of the other regular expressions. So this is what happens with R plus R prime. R dot R prime is basically concatenation. Therefore, we have not mentioned anything specific about that. This is just concatenation, and we will see an example for that very soon. Okay, so L of R dot L of R prime, so that is concatenation. R star is repetition. Okay, zero or more occurrences, rather, not even repetition. This is occurrence. Okay, so this R, whatever expression is there, it could occur zero or more times. This is similar to the regular expression that you see in grep, the grep utility. Okay, the basic BRE. Okay, so you have R star, which means that that expression could occur, that that regular expression could be there zero or more times. Okay, that is what star means. Now, so these are some examples. Okay, so but before that, I'll just show you this example, this tree, which is easier. So is this visible? I just wanted to get an acknowledgement. The audio is going through. uh, can anyone confirm if, because I'm not able to see that? Okay, yeah. Okay, thanks. Okay, so the idea is, see, on the base level, so this is like parsing, no? You might have heard about AST. For those of you who are interested, might read about that. Abstract syntax tree. So this is one of the most important aspects of programming language. I mean, programming languages are very complex, right? So and compilers, right? So how do compilers understand language, right? Like compilers are also programs, right? It means what it means. Nobody is going to like read through the code manually and understand what is going on, right? The compilers are automatic, right? So you have the programming language in a well-defined way you've written it, like syntactically valid, and then you run it. It basically creates your program out of it, right? How it happens? How does compiler understand whether the language is correct or not, and so on? So this is a very complicated process again, and so this is one part of it, the tree, right? And this is not even AST. AST is abstract syntax tree, which is specifically for programming languages, right? So this could be remotely related to that AST, but you get the idea, right? These things are basically building onto that. But the thing is, so this tree is for a regular expression. What happens is that you're trying to now understand the semantic of this. Okay, and semantics are again described as sets. Okay, so we are going to see that in this way. Okay, so we have this on the on the base level. You have only the alphabet, like the characters from that alphabet. So maybe I have ABC only, the very small alphabet A. I have ABC now. So this is at the base level. Now what are we doing? A star, right? So A star happens here at this level. Okay, so when star happens, right, so this is we are at this level. Similarly for B, star happens there, that's okay. And for C, this is getting added with this dot, which is concatenation. So we'll go one by one what is happening. We'll see at the base level we get only this, because L of A is what? Just the set A, having that later. No, L of B is what? You just got B there. L of C is C at this level. Okay, so we'll go one by one. So now here, after we are doing star operation on that. So A star is, again, what did we say? That L of A is the singleton set A itself, and then we are doing a star on top of it. So what it means is zero or more occurrences of whatever has been there so far. Okay, so it is only having A. Now we say zero or more occurrences, so this set becomes that. It could be phi also, like it could be epsilon means empty. It could be empty also, because we're saying zero or more occurrences. It could be zero also, therefore epsilon. A or A, and so on and so forth, right? It could keep on going forever. Similarly, B star happens, so it could be epsilon B, 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 and so on and so forth, right? It can keep on going, right, at this level. Now, moving forward, we are doing a plus now, right? So if we can come back to this expression, you see, right? So A star happened and B star happened, and then we are doing plus. So when we do plus, what happens? This is the union, right? So this is a set union. So we are taking union of this set. L of this set is, I mean, L of this so far up until this, L of this is this set, right? And L of the other expression is this. So we take a union now after doing plus. So we are taking a union. So A comes, B also comes, A, B, B, and so on and so forth. This is how you read it, okay? So at this point you have this. Now concatenation is happening with C. So C, you have what you have. C is only having this one element there. So after we take the concatenation, it becomes, because epsilon, see, epsilon goes away because epsilon concatenated with C, the empty string, and we are kind of concatenating with C, so we just get C. Epsilon is not there. It means this string cannot be empty. It has to have at least one C, right? You get the idea, right? So now with every element here, we are concatenating the element from the other side, this one. Okay, so it becomes C, A, C, B, C, A, A, C, B, B, C, and so on and so forth. This is what happens. Okay, so this one. Okay, now I'll go back to the description. So it says, now you understand, this is, these are the strings which can be generated by this regular expression. This is conforming to, these strings that are highlighted are conforming to the regular expression, like the language of this particular regular expression. Okay, part of, these are part of the language generated by the this particular regular expression. Now this says string of only A's and only B's. This is, which is correct, right? A could be occurring 0 or more times, or B. So this is like a choice. Okay, and you have to be careful about the parentheses. I'll explain it here also. So what it is saying is, see, it says I make a selection first. Okay, right? I make a selection and then, uh, you know, okay, let me think about it. Yeah. So here what happens is that I make a selection first and then I repeat. So it could be either A or B repeated 0 or more times. Okay, this part. Okay, whereas the other one, I'm just changing the track a little bit. I'll just come here. So I'll come back here later. Here the difference is, it is saying the choice itself is being repeated. Okay. So here you can only have A or B, and so on and so forth multiple times. Whereas here you can have A B, and so on, right? Because the choice is being repeated. Whereas there, here you make the choice first and then you repeat. Okay, so the choice comes first. You have to decide between A star and B star, and then you expand. However, here what is happening is A plus B itself is repeating. So A plus B, A plus B, A plus B, and so on and so forth. It can be multiple times. So now the choice is more choices are available. You understand the difference between this and that? Between A star plus B star and A plus B star, the whole star. Is that okay? Mm, okay, I'm assuming it's fine. Please feel free to unmute and acknowledge. Okay, fine. So that's what happens. Okay, so this is the difference. So it says strings of only A's or only B's because you make the choice first, right? I mean the choice is first and then you repeat, followed by C, of course, because then you're at the end you're concatenating with C. Here what happens is strings that contain the what A, B, B as a subword, because A, B is coming between, right? This one, this part, right? And then you have A, B, A or B, multiple times. So either way, it could be A. In the first choice you could have A, in the next choice you could have again A, and so on and so forth. So the choice is being repeated. Maybe I'll expand it and show. And similarly, so this one also. And since we only have two letters, C, A or B, right? We only have two letters. So therefore, it is every string that could be, because you can either have A or B, right? And A, B, B, this particular subword should be there, right? Because it is constant. It is given there in between. Okay. And if the okay, by the way, if the concatenation sign is not given, then you assume it is there. Like for example, A, B, B means A dot B dot B dot A plus B the whole star. And similarly, this side also. So A plus B the whole star dot A dot B dot A plus B the whole star. That is what it is, right? So if it is not given, you assume it is just concatenation directly. Okay, that is also okay. And then you have what else? Yeah, A plus B, the choice being repeated multiple times, and then you have a B, and then two letters after that. So therefore, it says strings were the third last letter because these two are the last letters, right? The A plus B and A plus B. These two are the last letters. After that, nothing can be there, right? So it is going to be either AB or BB or BA and so or AA, right? These are the four possibilities for the last two letters, right? So the B, then this B, the constant B is going to be the third last letter always. So that's what happens, right? And then you have in the beginning, it could begin with and then in the beginning it could be A or AB, and so on and so forth, because the choice is that is being repeated here. Okay, right? And similarly, B star means B could be there or could not be there also. So it says strings of B's that optionally begin with and end with A. So you have this A, right? A B star A. So it could be this one, This thing can occur zero or more times, or B itself could occur zero or more times, right? Or it could be both. So both are possible, right? The star makes it optional. That is one. Hopefully this is clear enough. I think I need to expand upon this, but for now, is it okay, or shall we go ahead and expand, develop it, or is that fine? Mm, am I audible? Okay, I think.
Yes, sir. Yes, sir.
Okay, fine, fine. So it's okay. I mean, yeah. So maybe we'll go through the example later. So that is the general idea of a regular expression. That's what happens. Now that was regular expression. Okay, so that was one part of it. The other is context-free grammar. These two we mentioned that we'll discuss, right? So here it is more simpler. Like it is simpler to understand. What happens is you've been given a starting symbol. Okay, so the left hand side is called a non-terminal symbol. Non-terminal. Everything on the left hand side here is non-terminal, like the capital letters generally. That is the notation. Okay. While on the right hand side, you may have a mix of non-terminal versus terminal symbols. What are the terminal symbols? Terminal symbols are those which are coming from the alphabet. So what do we have in alphabet? A and B, right? Only those two are terminal symbols, right? Now we could have a mix also. So what it is saying is we are going to do a derivation like this. Okay. So you always start with the starting symbol, and it will be mentioned what is the starting symbol. Generally, it is this. It is S itself, but it could be different also. Okay. So we start with this. Now S, what all I can follow from S? Like if I have S, what could it be changed to? Right? If you want to do, like if you want to proceed further, then what else it could become, right? So else S could become AX. That's what could happen. Right. So then I do derivation. S is becoming AX. Now the string itself is evolving in some sense. It's changing. Okay. Now what are the terminal symbols you get? Those cannot be changed. Those are like fixed. Okay. So from S you move to AX. That's okay. Now A cannot be changed. Now we have X, which is also non-terminal. So now we have these three rules. Either of the three we can follow. Either of the three. Once we have X, no. So I can follow rule number 2, for example. I'm starting from 1, 2, 3, 4, right? 4 rules are here. So I can do rule number 2 to mutate this X to AX. So this X itself will become AX. So the whole string will become AAX. Right? That's what happens. Or I can follow rule number 3 to make this X into BX. Or I could follow this fourth rule, which will just replace this X with B. So the final string will become AB. Now, as soon as you have a situation where you don't have any non-terminal symbols, everything has become terminal. So that is called a production. Okay, that is like the final string. Okay, so yeah, these are the productions. Yeah, this one. So you have AX. Now this X I replaced with. So I followed this rule, right? So I started with rule number 1. I had AX, right? Then I moved to rule number 3 because I had X. So I replaced this X with BX. So I got ABX. This one. Right. Once I had this, then I followed rule number 4. And which rule you follow is up to you. There's no order in that as such. Okay. Any rule can be followed any number of times. So you can even keep on doing this forever. So AX, and you can just keep replacing with itself. Okay. For as long as you have choices, you keep doing that. Okay. Unless it ends. And there's one more rule. Okay. The rule is you must end. So the first rule is that you have to start with the starting symbol. Okay, and then you can follow any rule, any of the rule. And the last thing is that you must end. So you cannot stop. You cannot stop derivation here. ABX is not a production, like it's not a terminal string. Okay, this is the only thing. So this ABB, we say then whatever production we get after doing all that, after finishing the derivation, what we get, we call it as part of the language of this grammar. This is a grammar actually. Okay, so whatever comes out of this by doing derivation, by doing this process of derivation, is part of the grammar. Now, if we do something which is not part of the grammar, then like it is not there. I mean, it's not like if there's some string which cannot be derived from this grammar following this rule, right? This rule, then it is not part of the grammar. So that is how we distinguish whether something is part of the grammar or something is not part of the grammar. Okay. So for example, consider this X, instead of following at the end, instead of B, it could have been A also, no? So then ABB will not be part of this grammar, then the changed grammar that I'm talking about. I could change this, right? I can change the last row, I can change. So instead of X going to B, I could make it X going to A also, right? So then it will not be, this ABB will not be part of the grammar because you cannot generate, because you have to end, right? So after this, I must either follow these three rules or go at the end. So at the end, I'll always have A then, right? Because I have to end, I have to end here only, right? Because after this only, we don't have any more non-terminal symbols. Okay, that clear? So that's what happens. So you get this. Okay, now the language then of this CFG G1 becomes the set of all terminal strings that can be generated by G. You understand this process of derivation? What all it could generate potentially is the set of all possible strings. So it could be infinite also, no? Because I can keep doing AX multiple times, or BX for that matter, anything, right? For as long as I wish, and then I end, and then finally I end. So this is like infinite. Okay. So that's what happens. Now some CFGs. Now I'll have to mention this. Some CFG, some. So CFG is a more broad. It's a more broad. What do you call notion? Okay. So here CFG. Some CFGs could be expressed as regular expressions, but not all regular expressions can. Rather, the other way around actually. Yeah. So all regular expressions can be expressed as CFGs, but not all CFGs can be expressed as regular expressions. Okay. That's what happens. So here, for example, G1 is having a corresponding regular expression, this one, but it might not be the case with all grammars. Okay, be careful with that. All CFGs, some CFGs can have regular expressions, but not all of them will have. But regular expressions, on the other hand, all the regular expressions mostly can be expressed using CFGs. Okay, and this is just a mathematical notation of what we are doing. Like we are just formalizing it. No, we're following the rules and so on and so forth. Okay, I'm not going to that notation. Basically, derivation happens whenever you have a rule, so you follow a rule, and then so I pick a rule from here, and then I follow that rule, so derivation happens. So shall not go into that. That will take time. And this one also is there, and the corresponding language is this. So to describe the language, this is the CFG, right? This is just the like the rules. Now the language generated by this is going to be a set, right? In general. So we have also used the regular expression to denote that language, but sometimes it may happen that CFG, it might be that it is not having a corresponding regular expression. Then you'll have to use a different method of expressing that language. But the idea is simple, right? This rule, whatever string follow these rules are part of this language, part of this grammar. Those strings which do not follow this rule are not coming from this CFG, are not part of the CFG, basically, right? Everything that could be derived is part of this. Okay, fine. Yeah, regular expressions can be written as grammars. That's okay, but the grammars, not all grammars can be written as regular expressions. So that is one thing that you need to keep in mind. Yeah. So again, same example, right? So think about it this way: stream, we are starting with that, for example, and then action could occur 0 or more times. Now, so action, you have a choice. So this is like having a choice, right? So either action G or action B, either of the two could happen, right? If action G happens, then action G can go to G. So G is a prefix, and then to S and N, right? So S and N, S could be a digit. So this power notation that we are using is for repetition. Okay. So this digit repeated either once, not repetition, rather the number of times you can have the digit. No, so it could be one digit or two digit or three digits. Whereas this power square, it means that digit twice. So that is the difference. 1 minus 3, this one hyphen 3 means either one or two times or thrice. Whereas this one says exactly two times you have to have that digit. Okay, so then what happens is G17, then, right, because you start with the stream, right? So you follow one action. So I followed act G. So then what happens is G is added as a prefix, right? And then you have S. So what all S could be? S could be a digit, either one or two or three. So that's what is happening here. So this is S, and this is N, then this is N. So this is G, this is S, this is N. Okay, what is N? N is a digit. Again, T is also a digit, and so on, right? S and T. Okay, so here we have, after we follow G, we can have S and N. So S could be a digit, which is the case here, and T, and then N. Basically, I'm talking about N, the last one. N is a digit. So this thing, have to occur twice, two times, and then you have a dot. This dot is not the concatenation, by the way. This is the actual dot. Okay, and then you have the digit again twice, and then you have the digit again twice. So this is what is happening. 0809190 is part of that grammar. And similarly, you have B13, 0627994, and so on and so forth. So this is like a grammar. Okay, right. So now I'll just describe the coverage criteria for grammars. Okay, so the thing is, terminal symbol coverage. What does it mean? Can you think about it? Okay, every terminal symbol, what did I say? Everything that is part of the alphabet, no, A, B, or if you have more characters, C, then the idea is that if you have this kind of a rule, right, every terminal symbol, meaning on the RHS, everything that you see in small letters, no, you must have these things. You must generate, in the test case, you must generate these things. You must cover for it. So I cannot have these many rules only. I must cover for C also. I mean, C also I have to cover because this is the terminal one, but there could be another terminal one also, no? So X can go to C, X can go to D also, assume that, right? So then I have to do for both C and D. So that is what terminal symbol coverage is. Terminal symbol coverage means right hand side, everything that you have, you generate grammar, you do derivation, you produce strings such that those are covered. So that's all. I mean, basically the idea is to produce strings such that this coverage is achieved, right? This criteria are met. Okay, so that's what you do. Okay, so you have to cover that. Terminal symbol coverage is the easiest one. Production coverage says everything that could be produced. So it is something like, every rule, every production that you could follow. Like I have to at least once follow this one and this one and this one also and this one and the last one. This is not about terminal symbol. All rules, all the productions that are possible, you have to follow that at least once. So that is production coverage. Okay, each production be in the grammar G. Derivation coverage says TR contains every possible string. Now this one is infeasible. Okay, why? Because again, I have X going to AX and I can keep doing this forever. So this becomes an infinite thing, right? So then you cannot have all derivations. Of course, I can express it as a set or something like that as a regular expression, but to generate all strings is not possible, right? So DC is infeasible. Yeah, DC is impractical, infeasible, because the number of derivations is infinite. Because you can have repeats, right? And so production, this one, PC, this D is a typo. Okay, this is just PC. So PC subsumes TSC. Why? Because the idea is on the right hand side you will have everything, right? Every terminal symbol, every possible terminal symbol will be there on the right hand side of every rule, every production. So since you are doing production coverage, you are implicitly doing terminal symbol coverage also. So PC subsumes TSC. Okay, and DC is infeasible. Okay, right. So that's what it is. Is that okay? Like these three, and hopefully you understood this part. Can I get an acknowledgement, please?
Yes, sir.
Okay, thanks. Okay, so this was syntax, right? And that we talked about. Now I'll go to mutation testing. Maybe I'll try to cover as much as possible today. Again, you have a recording. So I've done a detailed lecture on this one in the earlier terms. Also, we have that. You have that link given, so you can go through that to understand it. But then I'll try to cover what all I could this particular session. So again, now we have mutation testing. So we've talked enough about syntax and how they work. Whereas where is syntax coming from even, right? So we understood grammars. Like, okay, grammars are the things which are allowing us to define syntax and languages, and therefore we have all these things, right? Programming languages. So mutation testing. Now we're back to software testing in general, right? So it says, like, talking about source code. So it says mutation testing involves making syntactically valid changes to a software artifact and then testing the artifact. So I'll just spend a few minutes on this very line and understand what this is. So thing is, see, we talked about grammars. Now we said that we could generate invalid and valid artifacts, meaning if you think about source code, then it could be syntactically valid, syntactically invalid. Now for programming languages, right? So think about Java, right? If you make a syntactically invalid change, so you have a semicolon, for example, and you remove that from that statement, no? So then it will not even compile, right? So the idea in testing is that you have to check business logic, right? So our idea is to just check, whether the software is working correctly or not, and there are various ways of doing so. We had graph coverage criteria, we have graph based testing technique, we have logic based testing technique. Now we are talking about symbolic, and then we have mutation and so on and so forth. So mutation is one technique, right? The idea remains the same. We are trying to test the effectiveness of the software, and not only that, we are trying to see if our test cases are good enough. See, one can always come up and say that, okay, I'm going to do all my test cases manually. Okay, so the idea is not that only. The idea is in this test case design, how effective your test cases are. The whole, in terms of the essence of the very essence of software testing, is to come up with good test cases, right? Good tests. How do we define good tests? So that if it is a good test, it means it will be able to uncover potential, not only current faults in the software, rather potential faults, because software is an ever evolving thing. Okay, every day there are changes being made, not no not even in the everyday software that we use, be it operating systems or applications and so on and so forth. So every day things are coming up and changes are being made and so on and so forth. So it is good to have a good test suite, and most of the software does have that, no? So that when you run it, you are sure that it catches all, not only current faults, rather potential faults that might come in later because of changes. You are able to catch that. That is the idea of regression also, no? Regression testing. So the idea then is to come up with better test cases. Now, so the idea remains the same again. I have to do mutation so that I make good test cases. Now I will see how it is helpful. So, but mutation testing says that we are going to do syntactically valid changes. Why? So if you understand what I said just now, we are going to again have test cases, right? As a result of after all doing this mutation testing and everything. So if we do syntactically invalid changes, then it will not compile and then I cannot run it. So then I cannot test it. You see? So we are allowed to make changes, but we do it in such a way that it is syntactically valid also, at least. Right? Because see, syntactically invalid does not make any sense because we cannot run it, we cannot test it. So our objective is not fulfilled there. So what you have to do is to have make changes, but those are syntactically valid. And not only that, we are making careful changes, smart changes, so that our objective of coming up with good test cases is fulfilled. So we are not making arbitrary change, rather we are making careful changes, smart changes such that it is helpful for us in testing. Yeah, that is the idea. And then testing. So how do we know what is valid, what is not valid? Then we have to consider grammars. Like I know Java, so I know the syntax of Java. So in accordance to that, I'll do mutation. I cannot go and just delete that semicolon. It won't make any sense. From the perspective of testing, first of all. The other thing is that even if I am making some changes, I need to know the syntax. Then only I can accordingly make the changes, right? Right. And then again, we can use derivation in grammar also to generate invalid strings. That is also one thing. So this one is actually coming from that rule, no? That table was there. So S going to that, and X is going to that, and so on and so forth. So this one is saying about the grammar itself, meaning instead of the rule being X going to A, I can change it. I can change it from X going to A to X going to B. So I can change the grammar itself. So that is also one mutation that we could do. Okay. This is regarding grammars though. Okay. This is not regarding source code. And the testing based on these invalid and valid strings, whatever we get out of it, is called mutation testing. So we will see all of that. Okay. Now mutation testing can be applied to almost all software artifacts because this is general enough, right? Everything you have as text, which is having some sort of a rule to it, some semantic association, right? Then you understand, okay, what kind of changes are allowed, what are not allowed. So any text per se can be tested in that way, right? So it could be code, design, inputs, and requirements, and anything like that. Even requirements can be mutated. Okay. So that's what you have. Now, some terminology which is very important to understand because a lot of things are going to be building upon this. So the program that is being given to you, and now I'm going to talk about specifically about source code, okay? Even though it says string, okay? But we understand it in terms of source code because most of the discussion is going to be around source code only. It could be any artifact, but therefore we are saying string, but the idea is source code, okay? So ground string is the program, the source code of the program that is going to be tested. So developer makes the program, he or she gives the source code to you as a tester to test it. Okay. So the ground string becomes that the original thing, whatever the programmer gave to you. Okay. That is the ground string. Be it having, it could be having faults, it could not be having faults, anything could be possible, but that is the ground string for you. Okay. So that is part of course, and that is in the grammar. Why? Because the program is supposed to give you something which compiles. Then only as a tester you can test it, right? So then it is in the grammar, meaning it is valid, syntactically valid. So that is our ground string. Mutation operator is a rule that specifies syntactic variations of a string generated from a grammar. What it means in a nutshell is the source code, what all I could do to that source code, such that it remains syntactically valid. I could still compile and run that program, but no, I have made some changes. So what could be one mutation operator? So one condition checks A less than B, A less than B. I change it to A less than equal to B, right? I could do that. So that is still possible, right? So that becomes a one mutation operator. There are several mutation operators that we have. Okay. Now mutant means what is the resultant of that mutation. So you have mutation operator, you apply that, you do that variation. What you get out of that is called a mutant. Okay. So this is what you have. Result of one application of a mutation operator. So every time you modify it, you get another mutant. So the idea is you have ground string, you do apply mutation operator, and then you get a mutant. Then you go back to the ground string and apply another mutation operator, you get another mutant. Okay, so how many ever changes you do? We do it one at a time. So you do multiple changes, you get multiple mutants. Mutants are also programs which can compile. Okay, and ground string the original program. Mutation operator is the rule that allows you to do that. Okay, so I'll not go into the details of it because I think I mentioned it. Yeah, it could be a program specified using a grammar, meaning some language, and so on and so forth. Okay. So this we have discussed. Okay, this is again the same example. Now some invalid mutants are there. So right. So for example, this one is there, right? So now according to this grammar, you have these things are part of the grammar. Now valid mutants are something that you change, but it still remains part of the language. So this is very basic, right? So you had G17 080190. I made it 43. So instead of 17, I made it 43. But this could also be generated by the grammar. So this is in the grammar still, even after the mutation. So this mutant that I got after changing it, still part of the grammar. Okay. Whereas this is invalid mutation, like invalid mutant, right? Because 0801 is not possible. You have to have another this thing because it n says you have to have two, uh, uh, three times the digit twice, like two digits happening thrice, right? So that's what we have. This one is invalid, right? Because you are missing on that. Similarly, you cannot have 12 17 0 This is not. I changed it. So instead of b I made it 12, but this is invalid with respect to this grammar that is given, because 12 cannot occur first, because you have to start with the action. You start with the action, either you're going to go to act G or act B. So it is either going to be G or B. Okay. So you cannot have 12, for example, right? So if you change, something could be part of the grammar. If you change, it could be outside the grammar also. Okay. But the idea in source code is that you do changes such that it is part of the grammar, so that it compiles at least. Okay. Otherwise it does not make sense. Okay. Now we have defined some mutation operators uh, for all languages mostly. I mean, like for most of the languages, right? So Java, for example, we are having that, so that those operators are actually specifying rules which are potentially useful for us as testers. Okay, because I could make any arbitrary change, right? I mean, just like I could do anything, right? Which is valid also. Maybe I could do multiple things, but how do we know what is helpful for me, what is not helpful for me as a tester for testing this particular piece of code, right? I need to make changes which are thoughtful, right? In terms of uncovering faults, right? So therefore, mutation operators have been designed in such ways such that they are defined in, so if you apply them, then you know that those are useful. Again, this is a little bit subjective as to what you apply and what you don't apply. It depends on the situation, what kind of program you're trying to test on, and so on and so forth, because various operators are there. So it depends on what you're doing, but then some general operators are given. Now one thing I'll like to point out is, see, mutation testing, even though it's a technique, is not supposed to be used in isolation, meaning you're not going to do exclusively mutation testing everywhere. Then that is not the way it is supposed to be. Okay, some places you do mutation and test. Okay, some places you do that only. I mean, like as required. It is not as if you're going to do all in testing on based on mutation testing only alone. That is not how, and that is not how it is done. Okay, so some places we do that, and then according to that, whatever piece of code we are testing, maybe according to that we'll see if we figure out what is helpful as a mutation operator for me or not. Okay, so several of them are there. Now, a side note is this terminology that has been used in this mutation testing, that is part of the literature itself, but that is slightly off. I mean, it's not very uh, pleasant, but it's okay. I mean, we'll take it as whatever is given as part of the definition itself. So we'll take it as it is. Okay. So it says for a given artifact, let M be the set of mutants. Now you understand what mutants are, right? You have the ground listing, you're making changes to it, you're getting mutants, right? Multiple changes you make, you get multiple mutants. Now in mutation testing, each mutation itself, the mutant itself, is a test requirement. Okay, and the goal then becomes that in mutation testing is to kill the mutants by causing the mutant to produce a different output. Okay, so the coverage, in some sense, the reaching, the of that mutant, essentially coverage becomes killing the mutants. Okay, here. So and what is killing? It says causing the mutant to produce a different output. Now we have to understand what it means. Okay, so it says given a mutant small m belonging to capital M, all the various changes that you made, applied mutation operators, no, multiple times you are applying mutation operators to the ground string, and every time you're going back. Okay, so ground string, apply one mutation operator, then you go back to the ground string, apply another mutation operator, give it another mutant, and so on. So multiple mutants are there, right, for a derivation D. Okay, this derivation it is saying because it can be a part of the grammar also. So it's fine. We'll assume that it is part, because see, if something compiles, then it's part of the Java programming languages grammar, whatever grammar is there, right? So that's okay. So test is there again. Again, we came back to test case. Test T is said to kill the mutant, meaning I have done that coverage if and only if the output of T. Think about it. It's talking about the output now. Okay, output of T on the ground string. So this, assume this D is the ground string. Output of T on D is different from the output of T on M. So there is one test case. I made a mutation. I had the program ground string. I made a mutation. That's okay. So I got a mutant. I got a ground string. Now I'll construct a test case. Again, I'm constructing a test case. I create a test case maybe, and then I run that test case both on the mutant and the ground string. So the original program and my edited program, I'm running that same test case on both. If the output of the test case on the ground string is different from the output of the test case on the edited program, then I say that that mutant has been killed. Okay. So the essential objective in mutation testing is to kill all mutants. Basically, whatever changes you made, you must make sure that all of them produce different output on the edited version, meaning on the mutant versus on the ground string. So is this idea very, I mean, clear to all of you? This has to be very clear, I think. So just like to pause for a moment and let you all appreciate it. Is this okay? I mean, any questions so far? I think students have been silent. I don't know why today. Uh, any acknowledgement or
Sir, two things for silence, sir. One is
uh,
we understood everything, then
uh,
you have no questions to ask. Second thing
yeah,
is we don't understand
understand
anything,
anything?
still
Yeah,
don't
that
know what to ask.
yeah, the other case should not happen. If you don't
So
understand,
I
then
think
you ask.
as you,
You have to ask. Okay, so that's what happens. You modify it. So you understand, right? Mutation. Okay, so
the
let me take a
problem
step
is
back
I
and
have not yet gone through the lectures
hmm,
at videos. I'm
okay,
just
okay,
listening to you, sir.
okay. It's fine. I mean, it's been recorded also, so you'll come back and watch that again. It's fine. So the idea is again to be making changes and to the program that has been given to you and run a test case on it. That is the gist of it. Okay, you have a program. You make some changes to it. So you got two versions in some sense, right? So you have the original program and you have the edited program. Now you run a test case on both programs and see if the output is different on both. If that is the case, then the mutant is killed. Okay, so we'll see examples soon enough. Okay, if
But
that is not happening, go ahead.
I actually have a question in the graded assignment which I can't ask you
Okay.
because it's still
Oh,
not
it's
time.
not
Yeah.
over.
But
Okay.
see, the way I've understood the lecture versus how the problem is, it's
Hmm.
a little different. It's not about, for example, uh, uh, this thing of reachable and
Hmm.
not very clear. It's not about reachability, right? Because
It's not about reachable. Hmm.
you're doing a mutation, you want to check whether it will catch the mistake or not,
No, no. So
right?
it
So
it sort of connects to the idea of reachability in a certain sense. So the thing is why we are talking about even reachability here while we're making changes. See, the thing is, assume that you have a very big program. I mean, don't not even go there. So we have a small program. Let's say we have two branches, right? So I've got a if statement there, and then maybe it checks for number is prime or not. Then I go into if. If it is not prime, then I go to else and I do something. So in the if case, some computation is happening. Maybe I'm doing that number into two or whatever. And then else part, also something is happening, and then I'm finally printing it. Now, assume that I have the ground string. Now the programmer has made it. He or she has given it to me. Now I'm going to make changes. If I make changes in the if branch, I'm doing mutation testing. Okay, so I make something inside the if branch, then I must reach that mutant. No, I made some changes, but all my test cases, this test T, all my test cases are going to the else branch only. Then what does it mean to even change it? Right? So that's where reachability comes up. Whatever you have made changes, that should be reachable only. Then only it makes sense to then kill it and so on and so forth. Right?
okay,
So
okay,
that's what it is, right? Okay, and then the slight distinction we'll come to that, like weekly killing, installing link, all that we'll come to that. Okay, so don't worry about that. Okay, so now this one is very easy to understand. All changes that I have made gave me one mutant each. Okay, so the set of all such changes that I have made one at a time will give me this set M, which is these are my test requirement. What is the requirement then? How do I fulfill that? I'll fulfill that by constructing test cases such that all such mutants are killed. See, the essential idea is that we are saying whatever the programmer has given me, that is the actual correct program, and I am making mistakes into that program by mutating it and creating test cases such that if that mistake were to happen actually, naturally, that will be caught. That is the idea. So we are making mistakes in advance. That's what we're doing. Okay. So if the programmer had meant to write something else, if he or she were to write something else, then that would be caught. Okay. So we are improvising our test cases that way. Okay. We are making mistakes. So this mutation is somehow mimicking the mistake of a programmer. So that is even mentioned there. Okay. That is the idea. Okay. So then coverage. So we understand what killing is, right? I mean, basically, essentially, bring a test case such that it produces a different output, and which case it will produce different output, which case it will never produce different output, and so on and so forth. Like which case it cannot be killed, and so on. So we will see all that going forward. So the idea is
okay.
every mutant the requirement then becomes that you have to kill him. That is what mutation coverage is. Okay, every change that you made, you make sure you have test cases so that all such mutants are killed. So that is the coverage for you. Okay, and then this coverage is written as a percentage of like percent of how many. So how many ever mutants you made by making multiple changes in your ground string, multiple mutants you got, and how many ever are being killed using the current test suite that you have. So test suite have multiple test cases, right? Maybe I have 10 test cases, and let's say I've made 15 mutants, right? And my current test suite, 10 test cases are there. So maybe 8 to 10 mutants are being killed, but the rest of them are not being killed, right? So then I have to add more test cases so that those other mutants are also killed, right? So that is what the essential idea is. Now, one thing to note here is, and that's why we need operators. It says higher mutation score does not mean effective testing, because I can keep on making multiple changes. So I got ground string, and I'm just making multiple changes. Okay, and I'm having test cases also such that all those mutants are being killed also. So that's okay. But does that really mean that the testing is actually effective? No, because my changes are not useful, right? I'm just making arbitrary change, which is not useful, and then I'm able to kill it also. It's fine. But then again, I mean, how is it useful? How do you correlate the idea of having more mutation means more effective testing? It does not, right? And that's where we need operators. Operators are careful changes, not arbitrary. Careful changes. Okay, so I need to. So for example, I have a less than condition. No, I make it greater than equal to, because that could happen. No, in real life that could happen. Programmer meant to write less than equal to. So instead of less than, I make it less than equal to, and then test for it, right? So if that mistake were to happen, it will be covered, and so on. So for some careful operators are there. Even object oriented programming, you have interface and APIs and stuff like that. So you have mutation there also on the interfaces. If the integration is not correct, then some error will be caught, and so on and so forth. It could happen. Okay. Now, so this was mutation coverage. Okay, basically killing all mutants. Now, yeah, this again, this is not talking about source code itself, not the ground string. This is talking about grammar. So it's a detour. It's talking about grammar. So if the grammar is mutated, meaning that rule that is CFG, context free grammar. So if that is mutated, the testing goal is to see to run the mutation and see if the behavior is correct. Meaning again, mutation operator coverage is saying that for each mutation operator, TR contains exactly one requirement to create a mutated string M that is derived using the mutation operator. Meaning you change that rule, no? Like whatever rule you change, then you follow that production, the change rule, the new rule you follow, so that you produce a mutated string. That's what happens, right? And meaning for every operator that you could possibly have, like this one will not become clear now. You have to move forward and think about it, what operators are. But production also is similar, right? So production says for each operator that you applied, you got some new production, that is the change rule. Then you have to create a mutated string from that production. So basically, A, B example I gave. So I have to in fact go back quickly so that you could correct the dots. What I'm saying is this one. So assume that this is about grammar though. Okay. So assume that I'm having this CFG, right? Now instead of the fourth rule, right? So fourth rule, I have X going to B. So I could mutate it. No, this rule I could change. I could make it X going to A. Now what it is saying is mutation production coverage. It's saying that once you make that change, in that grammar, you must make sure that you use this rule somewhere. Like you do produce something using this. Okay, so that is what mutation production coverage is. Operator coverage is different. Like whatever mutation operator you're using to mutate it. Okay, so for every mutation operator that is there, uh, the different mutation operators that you have used, you make sure that you create a string that is that is derived using that mutation operator. So for this one to be appreciated, I think we have to go through the discussion of mutation operators also. That's okay. I mean, we can take it as it is for now. But by the way, this was about grammar. So most of the questions and discussion will be around source code. Okay, so we don't need to worry about grammars as such. Yeah. All right. So that's what. Okay. So number of test requirements for mutation is somewhat difficult because you don't know, right? I mean, how multiple changes are possible, multiple operators are even there. So what changes to make, how it is useful, and so on and so forth. So it is difficult to predict in advance how many test requirements you will have. Yeah, depending on what you have already applied. Let's say you have made 4 changes. Uh, you have made four changes. You have got 4 mutations. So that's okay. Like after you make it, but then before making it, like how to predict how many test requirements will be there is difficult. Okay. So it depends, right? How many operators are considered, because we cannot do everything. Some things we do. Some places we do certain things in certain places. Okay, in conditions, in loops. N versus n minus one. starting with 0, starting with 1, all such things, right? Okay, exhaustive mutation testing is not done. Yeah, some operators are there, we do that. Okay, yeah, mutation testing is difficult. Yeah, again, same thing, because we don't know in advance what to do. Okay, that's fine. This okay. Yeah, this is just a classification of what comes where. The BNF grammar is actually having, this is used to define programming languages and so on, compilers, and then you have specifications also, and then you can have input languages also like XML. So what happens is you have JSON and XML coming, in the API, REST API, modern application development course, you've done that, right? You have API input coming in, so you can mutate input also. Like some JSON is coming, and let's say a person information is coming, information for a person is coming, age is there, right? So that input that is coming in from that, I change that input, I made the age is like I change the age of the person, right? Something like that. So that is input space mutation, and so on. Similarly, you have program which is mutating programs. Integration, for integration, you have integration testing, operators for integration testing. Okay, and for specifications, you have FSM again. So that does model checking. We will see that. I think we are not going to go into detail of this one. Again, the same thing. What could be derived, what states could be followed. So that is the thing. And yeah, so we check for errors. So input space. So some data is coming for some user in a JSON format or XML, whatever, and then I change that input itself. Like I change the age of that person. And I try to register. That API call is going through, should throw an error, right? Because I changed that. So that's the idea. Okay. Yeah, program-based mutation is what we're going to talk about mostly. Okay, so be very careful with this one. Again, most of it I have described. We are going to begin with the program. That is our ground string. One or more mutation operators we apply. Suitable again. Suitable. What is suitable? You have to think about it. It's subjective. Okay, and program mutation must be program that compile syntactically valid mutation. Okay, mutants themselves are not tests. Be very careful. We have to kill that mutant. Mutants are edited programs in some sense. No? Mutated programs. We have to create test cases such that that is killed. And the definition of killing we have seen already. That is, you have to produce a test case such that when it is run on the ground string and the mutant, the output on the ground string of that test case is different from the output of that test case on the mutant. That is how you kill it. Okay. Now an example. So here what is happening? This is a ground string. Okay. This is a ground string. Minimum. Very easy. Int a, int b. Minimum value is this. Minimum value is equal to a. If b less than a, then minimum value is b. Of course, because I have initialized minimum value to a here, right? Now if b happens to be less than a, then I'll update it. So minimum value becomes b, and I'm going to return the minimum value, which is good. This works. Okay. Now I am doing a mutation. So this one is a mutation. So instead of this, so how do you read it is that this is no longer there. This statement is not there. This is mutated now. This statement, minimum value is equal to a, has become minimum value is equal to b. Okay. So this we have changed from a to b. Okay. Now this mutation happened. Now what happens in this multiple mutations we are applying also, we'll see that. So what it is doing is that it's replacing it. So instead of minimum value being a initialized with a, we are initializing it with b. Now what happens here now is that if b is the smaller number, okay, then that's okay. It will return the smaller number. Okay, but if a happens to be the smaller number, then it is never returned, right? Because minimum value is initialized to b. If b is not less than a, then you're not going to go, but regardless, you'll always return b. So a is never returned, right? So this is like an error that could arise, right? Initialization error could arise. So we have to construct a test case that this is killed, and it is easy to tell this one also. So how do we, for example, if a is greater than b in all test cases that I have for the ground string, so let's say 10 5, 10 5, right? So in the case of 10 comma 5 for a and b respectively, what should be the output? 5, right? So this ground program, what it will return? It'll return 5, because 10 5, right? So it will return 5. So that's smaller. A is larger. That's okay. Mm, Rather the other way around. Okay, so this, yeah, b is smaller. That's fine. Here also 10 5, 10 comma 5, I'm putting it, right? So minimum value is initialized to be a is never checked. What this program will return on 10 5, 10 comma 5, it will return 5. So what the ground string is returning? 5, no? And what is the mutated program returning? It is also returning 5. So the 10 comma 5, this input is not able to kill this mutant. Okay, this mutant that happened at this line mutation, that happened, this is not killed with this test input 10 comma 5. You have to give some test case such that it is killed. How we can have that case? We can have it, right? If we make a smaller and b larger, so you have a as, let's say, 20 and b as 100. Okay, so in the first case, what will you return? You return You'll return A, you'll return 20. That is correct only. In this case, you'll make it 100, right? Minimum value is initialized to 100, and B is less than A, which is not the case, but regardless, this will turn out to be false. This turn out to be false, and then you still return 100, right? So you return 100. So on 20, 100, this is returning 100, whereas this is returning 20, right? For this mutation. So therefore, this input is said to have this test case that have killed this mutant, this particular mutant. So wherever you have to give input such that both outputs become different. Okay, both the outputs become different. So if that happens, then that is killed. That is the idea. Is that clear? Is that okay? Any question? Go ahead, please. Okay, I'm assuming it's fine. So yeah, and several other mutations we are applying. So number one is replacing one variable reference with another A from B, and then number two is very basic. So instead of B less than A, we're making B greater than A. These kinds of changes we do. By the way, number three, you see, this is known as equivalent. Number three is equivalent mutant. Why? So in the ground program, what is happening? I have integer minimum value. Minimum value is initialized to A. Now I can say B less than A, right, on the ground string, or I could say B less than minimum value. It's the same thing, right? Because minimum value is referring to A. So regardless, that does not matter whether I say B less than A or B less than minimum value, right? So that number three, this is the change it is making, right? Number three. Instead of B less than A, it is making B less than minimum value, but that is equivalent in all test inputs. In all test inputs for this program, the left hand side, all test inputs, the output is going to be same as the right hand side for mutant number three. Only this. Okay, the rest of it remains as this. Only this change is made. Number three is made, and then it is equivalent because all inputs are going to be behaving the same way. The output will be same because of course it is logically equivalent, right? Instead of saying minimum value is equal to A, instead of saying B less than A, you can just say B less than minimum value. Under this case, when minimum value is equal to A, it's the same thing, right? So therefore, it is equivalent and so on and so forth. So there are some variants. Again, slightly odd terminology, but we'll go by that. So it says it is still bound mutant. It's the mutant of a program results in invalid programs that cannot be compiled. Think about it this way: as a Java, you have statements, you remove that semicolon, right? Now, mutant can this should not be generated. Like we are not interested in them because you cannot test it, right? If it cannot even be compiled, then there's no point in testing. Okay. Trivial is a mutant that can be killed by almost any test case. Like you make a very big change. I mean, as in something that could never arise, but you made something that will always result in a different one. So instead of returning minimum value, maybe you're returning a constant, some arbitrary negative or whatever. Like it's a completely different thing, right? So it'll always be producing a different. So that is called a trivial mutant. Like it is so different that for all inputs it is always different. The output is always going to be different, right? So instead of return true somewhere constant, you made it return false. So the output itself changes. So it is always going to be different. So therefore it will always be killed. That is trivial. Equivalent is that example that we saw, no? So B less than A, instead of saying B less than A, we can say B less than minimum value because minimum value is initialized to A, that is equivalent, right? So if that happens, functionally equivalent, no test case can kill them, of course, because for all inputs, it is exactly going to be the same on the ground string and the mutant. So how can you kill it? Then the definition of killing says you have to produce a different output, but since they are equivalent, you cannot have a different output, and therefore no test case can kill them. Okay, so trivial and equivalent are on both the other side of each other, so the opposites of each other in some sense. So you have trivial, which can be killed by any test case, right? Equivalent on the other hand cannot be killed by any test case. That is still bound is something that we don't need. So dead mutant is then are valid and can be killed by some test case. Okay, these are the only things that we need. Like the minimum example that we saw, right? This one, first one, yeah, this one. This is a good one because this one for some inputs produces the same output as the ground string, but for some inputs it does produce a different output also. So this we need to test, and that is useful for testing. Okay, so that is what happens. Okay, now we are going to refine it a little bit, but I'm not sure if we are going to cover this part today. So maybe in the next session we can continue.
Yes, sir.
Okay. All right. So I advise you all to go through the lecture also once again, and then again recording is still there. So we've gone through all this in the earlier sessions. Okay.
Okay, sir.
All right. Thank you. Thank you so much.
Thank you very much for today's session, sir. Thank you very much.
Thank you. Thank you. Bye.